Algebra 2, we've got 4B.4 today, transformations of polynomial functions, and this is something that we have seen quite a few times in our earlier chapters. We saw it in chapter 1 a little bit. We saw it more so come up in chapter 2. We were looking at graphs of quadratics, but now we're going to see it in chapter 4. The nice thing is it's the same concepts of shifts and reflections and stretches and shrinks. So let's have a look. The nice thing is the same rules apply. It's just they look a little bit different in this family of functions. All right, so our introduction. Consider the graph of f of x equals x cubed that's shown over here. Write a rule for each g of x that's a transformation of f. So this is just to kind of reacquaint ourselves with how graphs can change. And so for the first one, you can see in letter A, the graph of g, boy, it looks just like the graph of f, except it has been shifted. Instead of having that wiggle point at the origin, it is moved 2 units to the right. So I just want to think, okay, 2 units right, how does that look in a function? Well, for letter A, I would say that g of x is equal to f of x, but if we shift it 2 units to the right, that's actually x minus 2. Subtracting 2 to the input shifts 2 units to the right. So g of x for letter A is then not x to the third, but x minus 2. The input has changed to the third power. It's still a cubic function, right? That's the family that it belongs to, so the function still has that third power, but we had changed the input from an x to an x minus 2 to shift it to the shift it over to the right. All right, for our second g of x, you can see it looks exactly like f, except, and this, we could have a couple different ways of viewing this. When I look at this, I could say, hey, this is a horizontal reflection, or reflection over the y-axis. It looks like they took what was f of x and just reflected everything over the y-axis, either from right to left or left to right. In that case, if we saw it that way, we would say that g of x is equal to f of x, but to make a horizontal reflection, we make the input a negative x instead. So we would say that g of x is not x to the third, but we change the input to negative x to the third. Now, also, you may be looking at this and say, maybe you see the graph of g and you think, oh, they took the graph of f here and they just flipped everything vertically. What was up high is now down low and vice versa. So we could be thinking that g of x is equal to negative f of x, a vertical reflection over the x-axis instead. And both of those are correct. So g of x would then be a negative out in front of our f of x, in front of our x to the third. And both of these are equivalent, and here's why. This negative x to the third power means negative x times negative x times negative x. A negative times a negative times a negative means I end up with a negative product, and then we have x times x times x, x to the third. So these are actually equivalent. This is a question that would have 2 correct answers. Okay, but the idea is, this is kind of a special case, but the idea is those rules for reflecting graphs, they still apply, even though we're dealing with higher degree polynomials. So let's clear out, whoops, I meant to hit the eraser there. Clear out some of this stuff here. All right. For letter C, go orange, I got more colors to work with here. You can see we have the same shape of f, however, instead of that wiggle point happening at the origin, now it's been shifted up 2 units. So we are 2 units up. How do I show that with the transformations? Well, g of x just takes f of x, and if I'm going 2 units up, I add 2 to the output. So f of x, and then I add 2 afterwards. So g of x is going to take f of x, that was x to the third, and it's just going to tack a plus 2 on the end to raise the heights up 2 units. All right, that's probably the easiest one to grasp. All right, and then finally, letter D, here, this one, look at it, it's still doing what f of x did. It says falling to the left, rising to the right, so it hasn't like been stretched or shrunk or anything like that. It's simply been moved, that wiggle point again, from the origin, left 2 and down 1. Sorry, that's a shift. Left 2 and down 1. And if we were to write out those transformations in the function, to go left 2, we would add 2 to the input of f, and then to go down 1, we would subtract 1 from the output at the very end. So g of x is equal to not x to the third, but x plus 2 to the third, and then subtract 1. So again, the purpose of this introduction is just to take a look at one of our new higher degree polynomial parent functions, in this case a cubic, and explore the transformations, how those same rules can now be modified to work in this new environment. Now, just for reference in this chapter, this is just a reference section for you pretty much to have in your notes. We've got some examples of horizontal translations or shifts. We've got reflections over the x or over the y axis, horizontal stretches and shrinks, and vertical stretches and shrinks. Pay attention to these horizontal stretches and shrinks. Those are the ones that plague students year in and year out, just because it's the opposite of what you would think. So here, this 2x that's inside instead of just an x, that's a shrink horizontally by 1/2, even though we see a number 2 inside. Remember we said that means it's going 2 times as fast. So that's why it gets a lot skinnier. It takes up less time going left to right. Conversely, this 1/2 x stretches out. It's going half as fast. So it takes a lot longer to move from left to right. It stretches it out. But essentially, this section involves just a lot of substitution. All right, so our first examples just describe the transformation represented by g. So for number 4, here we start off with x to the 4th. Our function g takes that x to the 4th and adds 3 to it. That plus 3 was a shift up 3, or a translation up 3. Secondly, we start off with x to the 4th again, so a quartic function, and here we've multiplied a 1/2 out front of x to the 4th and then added 1. Notice there's nothing grouped in parentheses with our input, so all of the changes are vertical. They're happening outside that 4th power. The multiplying by 1/2 out front makes the graph half as tall, or we could say a vertical shrink by a factor of 1/2. And then the plus 1 at the end is a shift or a translation up 1. All right, and then number 16, our final example from this section. Again, we start off with our parent quartic function, our 4th degree parent function here. Now we've got a times 2 inside. See how it's grouped with the parentheses being raised to the 4th? That means it's a horizontal adjustment. And then a minus 3 outside. That times 2 inside means 2 times as fast, or a horizontal shrink by a factor of 1/2. If it's going that much faster, it's taking less time left to right, so it's going to be skinnier to make that happen. And the minus 3 outside, it's a vertical change. That is a shift down 3. It's always something that's really nice to have like a section like this in each chapter, where really the knowledge and the skills are the same that we've been practicing for a while now. It's just some minor adjustments to get used to this new family of functions. And we'll continue to see this as we learn more and more in chapters 5 and 6 and 7. All right, and it even comes up in chapter 9, I guess, too, if I were to be so brazen. So example 2, describe g as a transformation of f and write a rule for g. So here we've got a 5th degree polynomial for f of x. G of x is 3 times f of x. Notice that the 3 is multiplied onto the output. It's out front. It's a vertical adjustment. This is saying 3 times as tall. It's taking function f and making everything 3 times as tall. So g of x is going to take a 3 and multiply that onto every term of f. The x to the fifth, the minus 2x, and the plus 3, they all get tripled to make that height 3 times as tall. 3x to the fifth minus 6x plus 9 is our simplified rule for g. A lot of students will just put a 3 times x to the fifth, and they'll forget that, hey, every term gets made 3 times as large when we make that adjustment by multiplying a 3 out front. So we have to distribute. Number 20, here we've got a little bit more happening. We've got a negative x for an input instead of a positive x. That indicates a horizontal reflection. Okay, and then we're subtracting 5 afterwards. That means a shift or translation of the graph down 5 units. Okay, so let's take a look at what g of x then looks like. Instead of x to the fourth, I will have negative x to the fourth. Instead of x to the third, I'll have negative x to the third. I'll still have my minus 1, but then I subtract 5 afterwards to apply that downward shift. Now, one neat thing about inputs raised to powers, if the power is even, that means I will have a negative times a negative over and over and over again. So in this case, if I just imagine negative x times negative x times negative x times negative x, the fact that there's an even number of negative factors being multiplied together means the negative sign essentially gets absorbed by an even power. So x to the fourth, negative x to the third. Here this is an odd power term, so the negative survives. And we saw this when we did Descartes' rule of signs a little bit in one of the previous sections. And then negative 1 minus 5, that combines to make a negative 6. There's our simplified rule for g. Again, a lot of substituting and simplifying. That's pretty much it for this section. Example 3. Now we have to actually write a rule given the transformations that are written out as sentences. So we start off with this f of x. We're going to vertically stretch it by a factor of 2. So that's going to be the first thing I'm going to do. I'll show that work in blue. It's not going to be my final answer, so our final answer has to be g. I'll use function h as kind of like I call this one a stepping stone function. So a vertical stretch by a factor of 2 means twice as tall. So I'm going to take 2 times f of x to make that happen. That means h of x will be 2 times all the terms of f, like so, and we would distribute 2x to the fourth, now plus 4x and plus 12. Now that was only the first part. We got to follow that up with something else. 4 units to the right, we're going to transform this. This will lead me to my final answer. It's the last thing we have to do. G of x is going to take h where we left off our work, and to go 4 units to the right, that means my input changes from an x to an x minus 4. So instead of h being 2x to the fourth, it's 2 times x minus 4 to the fourth. And instead of being 4 times x, it's 4 times x minus 4, and then plus 12. And this right here is a perfectly acceptable place to end our answer. Actually, as a teacher, I almost prefer this because I can see where you've made that minus 4. Did you put that in all the right places? Some of you may feel inclined to distribute this 4 and combine like terms. If you want to do that, that's totally fine. But when we start seeing higher powers and then we do a horizontal shift like this, raising x minus 4 to the fourth power is quite a chore. That uses Pascal's triangle. So if we were to actually multiply all this out, it would be a lot of work. This is actually a very good place to end your answer for problems like this. So if it's something simple like combining like terms, please do it. But if it's something more involved like using Pascal's triangle, please don't feel like you have to do that. That's excessive. All right, next one in this set. Here we've got, wow, a 5th degree polynomial f. We're going to start off by reflecting it across the y-axis. Okay, now think, y-axis goes up and down, so if I reflect across that axis, that's a horizontal reflection. and it's a vertical stretch by a factor of 3. That's saying 3 times as tall. Now again, that's not my only job. I have to follow that up with something else, so I don't want to call this g yet. That's my final answer. So h of x is going to take function f, make it 3 times as tall, and it's going to make the input negative. So we've got the horizontal reflection and the 3 times as tall. Okay. And I'm just going to take my time here, make sure all those inputs of x are now changed to negative x, and make sure that I've got a 3 multiplying into all those. So that 3 is going to distribute 2 times negative x to the 5th. I'm not going to do 2 to the 5th. That 5th power is only applying to x. Since it's an odd power, it keeps its negative, negative 2 x to the 5th. Minus negative x to the 3rd. Again, that 3rd power just applies to this negative x. The negative survives, so minus a negative x to the 3rd makes plus x to the 3rd. Next, we have negative x to the 2nd. An even power will absorb the negative, so that's plus x to the 2nd, and then plus 4. And then finally, let's go ahead and distribute that 3 to make everything 3 times as tall. And then lastly, we have a very simple 1 unit down to get to g, our final answer. That's our last task before us. So g of x is going to take the function h that we just had and subtract 1 after to lower it down 1 unit. So that means g of x is going to equal negative 6x to the 5th plus 3x to the 3rd plus 3x squared plus 12, and then we subtract 1 at the very end. G of x, let's combine those like terms at the end. It's now just plus 11. Now, it is totally possible for you to go through this without writing out as many steps as I've done here. So for instance, you may just choose, when you get to this point, to just erase the plus 12 minus 1 and just call that plus 11 and box that up. That's totally fine. I just wanted to clearly show each step on this video. So please realize this is probably more writing than you would have to do to arrive at the correct answer. All right, and I believe that's the end of this. Yes, it is. So I hope you've enjoyed this section. Hopefully it's a nice little throwback to what we have been doing previously. And yeah, good luck with your homework on this section.